All right, we're in MyMathLab here. We're going to look at homework 2, which is on infinite limits, limits at infinity, and continuity. So let's begin by looking at a few questions. So this first one actually doesn't have to do with an infinite limit. This is just to remind you what is a limit as we approach some number from like the left or the right. So here we have what's the limit as x approaches 1 from the left of this function f of x. And notice here, as we approach 1, so here's 1, as we approach from the left, it's getting closer and closer to 4. So the left-hand limit is 4. If this had been a little plus here, limit as x approaches 1 from the right, as we approach 1 from the right, we're getting closer and closer to 3, right? But we're talking about a left-hand limit. So let's put 4, check our answer. Okay, the next one is going to involve an infinite limit. So we have the limit as x approaches 4 from the right of this function f of x. So notice here's 4 right here. As we approach from the right, notice the function values are getting bigger and bigger and bigger, right? So if I plugged in like 4.1, I would get a really big output, maybe 10. Or 4.001, I would get an output of maybe like 100 or 1,000. Okay, the closer we get to 4, the bigger our outputs are getting. So we have an infinite limit as we approach 4 from the right. Positive infinity. Now this one is really the same function, but we have the limit as x approaches 4 from the left. So notice we're plugging in numbers a little less than 4. We're getting outputs that are going down, 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 right? As we get closer and closer to 4 from the left. So plug in 3.9, 3.999. We're getting outputs that are way down here. So as we approach from the left, we get negative infinity. Now this next one says, refer to the graph of y equals f of x to the right to describe the behavior of the limit as x approaches negative 3 from the right. Okay, use negative infinity or plus infinity where appropriate. So what is the limit as x approaches negative 3? So here's negative 3 from the right. Well, as we're approaching from the right, this is going down, 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 down. So we get negative infinity here. Now, notice our answers here. It says select the correct choice. So we're going to put negative infinity. And you can see this little infinity symbol here. So we're going to put negative infinity. By the way, technically, an infinite limit doesn't exist. So technically, this limit does not exist. So we would put part B, but it says the limit does not exist and is neither negative infinity or plus infinity. But the limit is negative infinity. So again, technically it doesn't exist, but we're not going to put B down here. It does not exist because the reason it does not exist is because it's negative infinity. Okay, so hopefully the wording there isn't too confusing. Now, this next one is essentially the same thing, but it says limit as x approaches negative 3, not from the right, but just the ordinary limit, the two-sided limit. So what is the limit as x approaches negative 3? Well, notice as we approach from the left, it's going up to plus infinity. As we approach from the right, it's going down to negative infinity. So the left-hand limit would be positive infinity. The right-hand limit would be negative infinity. But the ordinary two-sided limit, we'll just have to say does not exist. So actually here we are going to put B because the limit does not exist and is neither negative infinity or plus infinity. Now, if they were both going up, right, from the left and the right, we would put plus infinity here. Or if they were both going down, right, we'd have a left-hand limit of negative infinity and a right-hand limit of negative infinity, then we put negative infinity here. But the fact that they're different, we have plus infinity and minus infinity, we're going to put does not exist here. Okay, now this next one has to do not with an infinite limit, but a limit at infinity. So here we're trying to find what's the limit as x approaches infinity of f of x. So we're actually not really interested in vertical asymptotes here. We're interested in, does this have a horizontal asymptote as we go further and further to the right? So as x approaches infinity, so if I plug in 4, I get a certain output. Looks like it's a little bigger than 1.5, maybe 1.6. If I put in 6, if I put in 10, if I put in 100, we're going to get outputs that are get closer and closer to, again, this looks like it's 1.5 here. So there's 1, there's 2. Right? We have this horizontal asymptote. So as x approaches infinity, this limit is going to be 1.5. Okay, this next one has to do with both infinite limits and limits at infinity. So it says the graph of g has a vertical asymptote at x equals negative 2. So that's what we see right here, this vertical asymptote there. And horizontal asymptotes, y equals negative 4. So this is what we see down here. And y equals 1, which is right here. Determine these limits. So what's the limit as x approaches negative infinity of g of x? So basically what's happening in the graph as we go further and further to the left, right? As x approaches negative infinity. So we plug in negative 5, negative 10, negative 100. What are those output values approaching? Well, notice it looks like they're approaching 1, right? We have this horizontal asymptote of 1. Okay, now what's the limit as x approaches infinity? Well, notice as we go further and further to the right, right, is our that what's happening to the function? Well, it's getting closer and closer to -4. The outputs are. So we'll have -4, where the limit as x approaches infinity. Now, what's the limit as x approaches -2 from the left? So here's -2. As our function approaches -2 from the left, notice it's blowing up to positive infinity. As we approach -2 from the right, it's going down to negative infinity. So -2 from the left, we're going to put infinity. -2 from the right, we're going to put negative infinity. And there we go. Okay, this next one says use the properties of limits to help decide whether the limit exists. If the limit exists, find its value. So what's the limit as x approaches infinity of this function? Well, really, the question is if you plug in values that get bigger and bigger and bigger, if you plug in x equals 10, x equals 100, 1,000, a million, what is this going to get close to? And the quick way of knowing what the answer is basically is if you have a rational function like this and it's a polynomial over a polynomial, if the polynomial on top has the same degree as the polynomial on the bottom, then you look at the leading coefficient. So notice it's a degree 1 polynomial here. It's a linear function. This is also degree 1. So you look at the leading coefficients, 2 and 5, and it's going to be 2/5 is our answer. In fact, let me check this answer, 2/5 here, or 0.4. But actually, let's go into Desmos and see if we can understand this a little bit better. Here's our function f of x equals 2x over 5x minus 5. Notice, like, what's f of 10? Okay, it's 0.4 repeating. Now, why is it 0.4 repeating? Well, if you plug in 10, notice you get 20 over, is it 45? Right, 20 over 45, that's 0.4 repeating. Or what's f of 100? Okay, it's this. Notice that would be 200 over 495. Let's try that here. 200 over 495. Notice that's the decimal. But what happens if we plug in 1,000 or 10,000 or 100,000 or a million? Well, notice my outputs are getting closer and closer to 0.4. In fact, you could see that on the graph here, right? Notice when my inputs get bigger and bigger and bigger, what are those outputs getting closer and closer to? We can even zoom out further here, right? As my input is, say, getting up towards 20, notice my output's getting close to 0.4, right? And the further we go to the right, the closer it's going to get to 0.4. In fact, this has a horizontal asymptote, y equals 0.4, which is 2/5, right? 0.4 is the same thing as 2/5. In fact, let's make this asymptote here. You can see the asymptote here. So the limit as x approaches infinity of this function is 2/5. And again, the quick way to do this is if you have a polynomial where the degree on the top is the same as the degree on the bottom, you can ignore all the lower degree terms. We can essentially just ignore this -5 and just look at the 2 and the 5 there. Well, let's do a similar one here. What's the limit as x approaches infinity of this? Well, again, we have a degree 2 polynomial on top and a degree 2 polynomial on the bottom, right? They're both quadratic. So we can ignore these lower degree terms. We can ignore the 7x minus 9. We can ignore the plus 2 and just look at the 5x squared and minus 6x squared. In fact, really just look at 5 and minus 6. So it's actually -5/6 is going to be the answer. Okay, and you could check if you were to graph this function f of x equals this, it would have a horizontal asymptote y equals -5/6. And by the way, that would work whether we're approaching infinity or negative infinity. Okay, if you have a rational function, right, a polynomial over a polynomial, if you have a horizontal asymptote going off to the right, you're going to have that same horizontal asymptote going off to the left. So this would also be true even if we said let x approach negative infinity. Okay, now what about a situation like this? Notice here we have a degree 3 polynomial in the numerator and a degree 4 polynomial in the denominator. So the degree of the denominator is bigger than the degree of the numerator. In this case, y equals 0, or in other words, the x-axis is going to be a horizontal asymptote. So this limit is going to be 0. Essentially what's happening is as you plug in these x values that approach infinity, like 10, 100, 1,000, a million, the denominator is going to get big much, much faster than the numerator gets big. So the fraction is going to be kind of lopsided toward the bottom. The bigger the x is, the much more lopsided it will be so that you're going to get huge denominator compared to the numerator. So that fraction as a whole is going to get smaller and smaller and smaller. So they're going to have a limit of 0. Now, notice in Desmos here, f of x equals this. Notice we have, as we go further and further to the right, and same thing as we go further and further to the left, our values, our output values are getting closer and closer to 0, right? We have y equals 0, or the x-axis is a horizontal asymptote. Notice for this big value input, 17.2, the output is 0.06. And if we were to go further and further to the right, our outputs are going to get even closer and closer to 0. Again, because the denominator is sort of overpowering the numerator. Now, what about something like this, where we have a limit as x approaches infinity, but of a rational function, but the degree of the numerator is bigger than the degree of the denominator? Well, the fraction is going to get more lopsided toward the numerator. Again, we can kind of ignore all the lower degree terms here and just look at the 6x cubed and the 8x squared. As x approaches infinity, what's going to happen to this? Well, it's going to blow up. Okay, so we're going to get an infinity, and the question is, are we going to get positive infinity or negative infinity? And so here it really matters, are we approaching positive infinity or negative infinity? And also matters about our terms here. So do we have a negative coefficient up here, negative down there? So the way I like to think about it is, as x approaches infinity, imagine just plugging in a big number for x. Let's say like 100 for x. If you plugged it in here, 100 cubed, that's positive, times 6, that's positive. So you get a big positive number down there. Well, if you plug in 100 there, 100 squared is positive, times 8, that's positive. So when you divide those out, you're going to have a positive over a positive. And again, you could ignore these lower degree terms, because as x gets bigger and bigger and bigger, these lower degree terms don't matter so much. So the fact we had positive infinity up here and a positive down there means it's going to approach positive infinity. Okay, now it'd be different if, let's say we're approaching negative infinity. If I were to plug in like negative 100, well, negative 100 cubed is actually a big negative number. Okay, or it would be different if we had like a negative coefficient here instead of 6, maybe if we're a negative 6 or negative 8 down there. But our answer here is plus infinity. Okay, and here's the graph of the function. Notice as we go off to the right, notice our graph goes up, 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 up. So whether we zoom out here, nothing else interesting is happening over here. It's not going to trail off. It's just going to go up, up, up. And same thing as we go to the left, it's going to go down, down, down. So notice the limit as x approaches infinity of this function, as our inputs get bigger and bigger, our outputs are also getting bigger and bigger and bigger, right? They're approaching infinity. And if, as we approach negative infinity, the outputs would approach negative infinity. Okay, now again, 17. The degree in the denominator is bigger than the degree of the numerator. What's the limit as x approaches infinity? So again, we can ignore the 5x, the 10x cubed plus 2. By the way, we could not ignore those if we were doing like the limit as x approaches 7 or the limit as x approaches 0. We couldn't ignore these terms. But the fact that we're approaching infinity means these terms are going to get overpowered as we approach infinity. So again, the degree in the denominator is bigger than the degree of the numerator, so the answer is just going to be 0. Okay, here we have the same degree in the numerator and denominator. Again, rational function. It's a linear function on top, linear on the bottom. So we can just look at the leading coefficients. So the leading term there is 6x. The leading term there is 2x. The leading coefficient is 6 and 2. So we're just going to get y equals 6 over 2. So our answer is going to be 6 over 2. Now, it says type an integer or simplified fraction. If I type 6 over 2, it'll probably be wrong because it has to be simplified. So it's just 3. And by the way, the answer is not the limit does not exist, right? The answer is 3. Okay, let's look at this one. Find, part A, the leading term of the polynomial. Part B, the limit as x approaches infinity. And C, the limit as x approaches negative infinity. So remember that the leading term is not the term that appears first necessarily, like the 20. It's the term that has highest degree. So that the highest degree term is negative 8x to the 7th. That's the leading term. By the way, the leading coefficient would be negative 8. Okay, but the leading term is negative 8x to the 7th. Now, what's the limit of p of x as x approaches infinity? So as x gets bigger and bigger and bigger, what's the limit as x approaches infinity of this? Well, again, we can ignore these lower degree terms. As x gets really big, as we approach positive infinity, imagine plugging in a really big positive number for x. Let's just say 100. Well, 100 to the 7th power is a huge positive number, but then when we multiply it by negative 8, it's a huge negative number. And 100 to the 6th power is not nearly as big as 100 to the 7th power. So again, these lower degree terms aren't really going to affect the answer. So the answer is negative infinity. Okay, now what's the limit of p of x as x approaches negative infinity? Again, we could ignore these terms here, but as x approaches negative infinity, now imagine plugging in a number like negative 100. Okay, well, negative 100 to the 7th power is going to be a really big negative number, right? We're raising it to an odd power. So negative 100 times negative 100 times negative 100. Do it 7 times, you're going to get a really huge negative number, but then you're multiplying by negative 8, so it's going to be a really big positive number. So we're going to get positive infinity. Okay, this is a similar type one. What's the limit as x approaches infinity of this? Well, again, we could ignore these lower degree terms. So as x gets bigger and bigger and bigger, if we're approaching positive infinity, we plug in a really big value for x, like 100, 1,000, a million, something like that. A million to the 7th power is just going to be astronomically large. It'll be huge. Multiply it by 2, it'll be even bigger. So notice we're getting infinity. By the way, technically an infinite limit does not exist, but we don't want to put part B. The limit does not exist and is neither negative infinity or plus infinity. So the limit doesn't exist, but the reason it doesn't exist is because it's infinity. Now this one says, find the horizontal and vertical asymptotes of f of x. So what are the horizontal and vertical asymptotes? Well, as x approaches infinity, just like these previous problems we've been doing, notice it's going to have a limit of 4. Right? The limit as x approaches infinity of this is going to be 4 because we have linear up here, a linear function down there, right? Degree 1, degree 1. And look at the leading coefficients. So the coefficient of x is 4. The coefficient of x there is 1. 4 over 1 is just 4. So it's going to have a horizontal asymptote. Now it says type an equation. We're not just going to put 4. We want to put y equals 4. In fact, let's look at this function in Desmos. We have f of x equals 4x over x plus 1. Notice as we go further and further to the right, this is getting closer and closer to 4. In fact, let me type in y equals 4. Okay, we're going to get that horizontal asymptote. Let me change the color here to blue and make it a dotted line. So notice there's y equals 4. Okay, that's a horizontal asymptote. Notice we also have a vertical asymptote. Where is that vertical asymptote occurring? Well, it's going to occur at a place where the denominator is 0. Okay, notice the denominator is 0 at x equals negative 1. So negative 1 is going to be our vertical asymptote. And actually, I should say x equals negative 1. That's the equation of our vertical asymptote. Okay, so the horizontal asymptote, you don't just say 4, it's y equals 4. Remember, y equals a number is a horizontal line. X equals a number, like x equals negative 1, is a vertical asymptote. Okay, so we can zoom out and see these two asymptotes. So let's plug in our answers. The function has one horizontal asymptote. Again, don't just put in 4. It says type an equation here. Always make sure to read what's in blue. Check our answer. Part B, find the vertical asymptotes. Okay, so does it have one vertical asymptote or has two vertical asymptotes or no vertical asymptotes? Well, it has one, and it's x equals negative 1. Okay, it's the value of x that makes the denominator 0. Okay, now let's look at this next one here. Find all horizontal and vertical asymptotes. And here is our function. So what are the horizontal and vertical asymptotes? Well, the horizontal asymptote is actually pretty simple. It's just going to be 9 over 1. Y equals 9 is going to be our horizontal asymptote because, again, we have a degree 2 polynomial here, degree 2 polynomial there. We look at the leading coefficient here and here. So it's y equals 9 over 1. But don't put 9 over 1 because that's not simplified. Just put y equals 9. Now, what about the vertical asymptotes? Well, you need to find the values of x that make the denominator be 0 and also make sure that they don't cancel with anything on the top. So notice we can factor x squared minus 4 to be x plus 2 times x minus 2. So notice that 2 and minus 2, both of those values would make the denominator be 0. But also, it's nice to factor the numerator because if we were to have an x minus 2 factor, let's say in the numerator, that would cancel with this factor down here. And then at 2, we would not have a vertical asymptote. We'd have a hole in the graph. But it turns out, though, this can't be factored. There's no zeros of the numerator, and the reason is because it's kind of like a sum of squares, right? You can factor a difference of squares, x squared minus 4, but you couldn't factor sum of squares, x squared plus 4, because there's no value of x that can make that 0. Notice 9x squared is never negative. It's always greater than or equal to 0. And when you add 4, then this is always going to be bigger than or equal to 4, no matter what your input x is. So it doesn't have any zeros. You can't factor it. Unless you use imaginary numbers, I guess you could factor it. But the point is, neither of these factors will cancel with a factor on the top. So our vertical asymptotes are going to be x equals 2 from this one right here, and x equals minus 2 from this one over there. In fact, notice on Desmos here, we see y equals 9 is a horizontal asymptote. And we see that x equals 2 and x equals negative 2 are the vertical asymptotes, right? We have vertical asymptotes at 2 and negative 2, and we have this horizontal asymptote y equals 9. So let's type it in. It has one horizontal asymptote, y equals 9. And it has two vertical asymptotes. So what we're going to do right here is not do part A. We're going to put B here. It has two vertical asymptotes. The leftmost asymptote is x equals negative 2. And the rightmost vertical asymptote is x equals 2. And again, it says type equation. So make sure to not just put 2 or negative 2 and 2. Okay, what about right here? Find the horizontal and vertical asymptotes of this function. Well, notice the degree on the top is bigger than the degree on the bottom. So as we approach infinity or minus infinity, we're going to get infinite limits. So there's actually not going to be any horizontal asymptote. So whenever the degree on the top is bigger than the degree on the bottom, there's going to be no horizontal asymptote. And this one actually, I don't think is going to have any vertical asymptotes either. In fact, it's not, because the denominator can't be factored. There's no zeros of the denominator. There's no value of x that you can plug in here that'll make that 0. Any value of x that you plug in here is going to make that positive, right? Whether the input x is positive or negative, raise it to the fourth is positive, add 2, it's even more positive, right? And so it's not going to have any zeros. So there's actually going to be no vertical asymptotes either. In fact, just checking Desmos here, this is what the graph of the function looks like. And nothing interesting is happening way over here. We're not getting vertical asymptotes over here or here, right? We zoom out. In fact, notice this looks a lot like y equals x squared. Right? Notice the graph looks a lot like y equals x squared. Why does it look so much like y equals x squared? Well, because again, if we kind of ignore this plus 2, we ignore the lower degree terms, then notice we have x to the 6th over x to the 4th. Well, x to the 6th over x to the 4th, it's x squared. So notice it looks a lot like x squared. And as we go further and further to the right, it looks more and more like x squared. For these small values of x, the plus 2 kind of matters. That's why it's not nearly, that's why the graphs are off a bit in here. But the graphs are really close out here. So notice there's no vertical or horizontal asymptotes. Okay, what about this one? Well, notice the degree on the degree in the bottom is bigger than the degree on the top. So notice as we approach infinity, as x approaches infinity, the outputs are going to get closer and closer to 0, right? So it's going to have a horizontal asymptote y equals 0. Essentially, the x-axis is going to be the horizontal asymptote. Right? If you put in really big values for x, the denominator is going to overpower the numerator, so the fractions are going to become lopsided toward the denominator. So the outputs are going to get closer and closer to 0. And again, that'd be whether we approach positive infinity or negative infinity, where we'll have that same horizontal asymptote. Now, what about vertical asymptotes? Well, again, this one can't be factored in the denominator, and so we're going to have no vertical asymptotes. What about this? Find the horizontal asymptote, if any of this. Now, I'm glad it's asking about a horizontal asymptote rather than a vertical asymptote, because the horizontal asymptote, this one's going to be pretty simple. Notice we have a degree 3 polynomial here, degree 3 polynomial there, so we just look at those leading coefficients. So it's going to be y equals 2/9 is going to be the horizontal asymptote. So as we approach infinity or negative infinity, y equals 2/9, which is 0.2 repeating. That's going to be the horizontal asymptote. Now, why am I glad it's not asking about vertical asymptotes? Well, because we would need to factor this. Okay, and it's a cubic polynomial. You need to factor it to be able to find where those vertical asymptotes are, if there are any. Okay, now this one is saying find the vertical asymptotes of the graph of this function. So how do we find the vertical asymptotes of this? Well, notice the values of x that make the denominator 0 are 9 and -3, right? If we plug in 9 for everywhere we see an x, or -3 everywhere we see an x, we're going to get a 0 down here. So x equals 9 and x equals -3. That's our first guess, although we do have to be slightly careful. In fact, for this one, it's a good idea to factor the numerator. So notice this is the function that we had. The numerator factors would be x minus 10 times x plus 10. That's a difference of squares. But notice neither of these factors gets canceled with a factor up there. If this had been, say, like x plus 3 right here on the top, this x plus 3 and x plus 3, that would get canceled. And we would not have a vertical asymptote then at x equals -3. What we'd have is a hole in the graph at x equals -3. Now, we'd still have a vertical asymptote at x equals 9. But if you have something that cancels with something else, right? If this factor here cancels, we'd have a hole in the graph rather than a vertical asymptote. Okay, so notice we have it 9 and -3. Oh, and by the way, it's not y equals 9, y equals -3. It's x equals 9, x equals -3, right? They're vertical asymptotes, vertical lines there. Okay, now what about this one? Find all horizontal and vertical asymptotes of this. Well, the horizontal asymptote is actually going to be pretty easy, right? It's a degree 2 polynomial. So we look at the leading coefficients, which are 4 and 1. So our answer is going to be y equals 4 over 1. But again, don't put 4 over 1, just put y equals 4. Okay, type an equation. It may mark it correct if you put 4 over 1 because it didn't say simplify. But let's simplify. Y equals 4. You do want to put y equals 4 rather than just 4, though, right? Type an equation. Okay, now the next one, find the vertical asymptotes. Well, what we need to do is to factor the denominator. And I went ahead and factored the denominator. Notice it's x plus 6 times x minus 4. If you FOIL that out, x times x is x squared. You have a plus 6x, a minus 4x. That gives you plus 2x. And 6 times minus 4 is -24. Now, it's also important here to factor the numerator. And this is a little trickier to factor because we have a coefficient of x squared that's not just 1. We have a 4x squared. So we want to write it as 4x times x to give us a 4x squared, right? 4x times 4x is 4x squared. We have a 4 times 4x, that's 16x, minus a 1x, that gives us the 15x, right? So 4 times 4x is 16x, minus 1x is 15x, and minus 1 times plus 4 is minus 4. Now, notice, if this had been a minus 4, that would cancel with this. But the fact that it's a plus 4 means it doesn't cancel. So we're still going to have these vertical asymptotes, x equals -6 and x equals 4. So right here, the function has two vertical asymptotes. The leftmost asymptote is x equals -6. The rightmost asymptote is x equals 4. Now, for this one, it actually looks really similar. I think in this one, if you factor it out and you factor this, I think one of the factors actually does cancel. So I think in this one, if you work it out, I'm not going to work it out here, but if you work it out, one of the factors cancels, and so you're actually only going to have one vertical asymptote. Now, your horizontal asymptote looks like that would still be y equals 4, I guess, in this case. But for the vertical asymptote, I think one of those cancels. So you do have to be careful to factor the numerator. Okay, find the vertical asymptotes of the graph of this. Well, what we need to do is to find the value of x that makes the denominator be 0. So notice right here, I factored the denominator. 5 times x plus 30, we can pull out a 5. It's 5 times x plus 6. Now, I also factored the numerator. It's 3 times x minus 3. But notice that x equals -6. That's going to be our vertical asymptote. By the way, we'd have a horizontal asymptote, y equals 3/5. By the way, you might wonder, what is this 3 doing up here, right? If we plug in 3, we get a 0 in the top. That would be an x-intercept of the graph. Okay, that would be a 0 of the function, or an x-intercept. Okay, but when we're talking about vertical asymptotes, though, we're just looking at the values of x that make the denominator be 0, as long as they don't cancel with factors in the numerator. So x equals -6 should be our vertical asymptote. Okay, so x equals -6. And again, you could see that probably just by plugging in it's -6 is the value you need to plug in there that will make that 0, right? 5 times -6 is -30, plus 30 is 0. Oh, and here's the graph of that function. So notice we actually have y equals 3/5 is our horizontal asymptote, right? Our vertical asymptote, though, is x equals -6. And notice, by the way, right here, that number 3 that I was telling you about, actually at 3, that's where we crossed the x-axis, right? That was the value of x that made the numerator 0. That's our x-intercept. All right, here we have the limit as x approaches -10 from the left of this function 1 over x plus 10. So what is that limit? Now notice if we just plug in -10 here, we get 1 over 0, which is, it's kind of like it's infinity, right? But it's undefined. So what is the limit as x approaches -10 from the left? Now, when we're approaching -10 from the left, think on a number line here, right? If you had a number line here, so here's -10 on your number line. If we're approaching -10 from the left, we're plugging in values like -10.1, -10.01, -10.001. If we were approaching from the right, we'd be plugging in values like -9.9, -9.99999, right? So we're plugging in numbers a little to the left of -10, like -10.1. Well, notice if you plug in like -10.1, right? -10.1 plus 10 would be -0.1. Okay. And what's 1 over -0.1? Well, it'd be 1 over a tiny number is actually going to be a big number. And you put a negative in front of it, it's negative in front of it, it's going to be a big negative number. If we plugged in like -10.000001, well, -10.0001 plus 10 would be -0.0001. So what's 1 over -0.0001? It'd be a really huge negative number. So it looks like our answer is going to be -infinity. Okay, I think if we approach from the right, okay, if we approach -10 from the right, we plugged in like -9.999 plus 10, that would actually be positive 0.0001. And 1 over 0.001 would be a really big positive number, and we'd end up getting plus infinity. In fact, here's the graph of 1 over x plus 10. Notice it's really like the graph of 1 over x only shifted to the left 10. So notice that we have this x equals -10 is our vertical asymptote. And notice as we approach -10 from the left, we're going down to -infinity. As we approach -10 from the right, if we plug in those numbers like -9.999, we get really big positive numbers. As we approach from the left, we're getting really big negative numbers. Now the question asks about approaching -10 from the left, so we're going to get -infinity. Okay, now the rest of the questions are asking about continuity, and I think most of these are actually pretty simple and pretty straightforward, pretty quick. So this one says the graph of a function f of x is shown. Is f continuous at x equals 1? Okay, well, notice this is not a continuous function overall. We have an issue there. So in fact, here's 5, 4, 3, 2, 1, 0. We have an issue at 0, right? It has this jump discontinuity. But at x equals -1, right? At x equals -1, it's continuous, right? So at -1, there's no problem with the function, right? So this is continuous at -1, even though the function overall is not continuous. Okay, what about this one? Is this function continuous at x equals 2? Okay, now again, this function actually is continuous everywhere. There's no issues with this function. There's no holes in the graph or vertical asymptotes, anything like that. Even here where there's a sharp corner, it's still continuous there. But at 2, is it continuous? Yes. Check our answer. There we go. Now, what about this one? Use the graph to answer the question, is f continuous at x equals 0.5? 0.5 here. Well, there's 2, 4, 6, 8. Here's 0. Here's 1. 0.5 is right here. And yeah, that looks like it's a bad place, right? That looks like it's a place where we have a discontinuity at 0.5. So the answer would be no, it's not continuous at x equals 0.5. It's continuous pretty much everywhere else. I guess it is continuous everywhere else. But at 0.5, x equals 0.5, that's where you have discontinuity. So is this continuous? No. Okay, now what about this one? Use the graph to answer these questions. Find the limit as x approaches 4 from the right, that's what the plus means, of f of x, and find the limit as x approaches 4 from the left of f of x. So again, this is not positive 4 and negative 4. This is positive 4 in both cases here, but we're approaching from the left, from the right or from the left. And then part B, what's just the limit as x approaches 4, the two-sided limit. So let's look at our graph here. So notice 4 is right here. So there's 0, there's 10. So 4 is right here. Notice as we approach 4 from the left, right, if we put inputs like 3, 3.5, 3.9, right, notice our outputs are going to get closer and closer to, looks like this is 4 here. 1, 2, 3, 4. Yeah. So as we approach from the left, it's looking like we're getting 4 as the limit. As we approach from the right, it looks like we get 5 as the limit. Okay, so as we approach from the right, it's asking first, we get 5 as our answer. And as we approach from the left, we get 4 as our answer. Let's check our answer. And what about for the two-sided limit? Limit as x approaches 4 of this function. Well, we're going to have to put does not exist. So don't just leave it blank. Make sure you click does the limit does not exist. Right? So the limit does not exist. So the question then is, what's f of 4? Okay, what's f of 4? Well, notice f of 4 is 4 here. So if we input 4, we get an output here of 4. So f of 4 is 4. By the way, it says the other option is the function is undefined at 4. Well, if this were an open circle here and an open circle there, then it would be undefined. But f of 4 is 4 in this case. And now the last question, is the function continuous at 4? Why or why not? Well, remember, to be continuous at 4, we need to have the limit existing, right? So the left and right hand limits have to both exist and be the same. But notice they're not, right? The left and right hand limits are not the same. So the limit did not exist. So in fact, that's what we found in part B. The two-sided limit did not exist. So therefore, it can't be continuous. Now, even if the two-sided limit did exist, it's possible it would be discontinuous, because what you need to have happen is not only the limit as x approaches 4 of f of x has to exist, that actually has to equal f of 4. So what we can say is no, f is not continuous at 4 because this limit does not exist. Okay, it's not these answers that would say yes, it is continuous at 4. And it's not this one, no, f is not continuous because f of 4 is undefined. Well, f of 4 is defined, right? It's defined to be 4. So that's just making sure that you understand the definition of continuity. Now, the next couple are about continuity on an interval. Is the function continuous on the interval -5 to 5? So notice there's no, on this whole interval, -5 to 5, is it continuous at every single value? Is it continuous at -2? Is it continuous at 4? Yeah, notice it's continuous at every value between -5 and 5, right? There's no discontinuities. So yeah, this is continuous everywhere on that interval. Now, what about something like this? Use the graph to answer the question, is f continuous at x equals 1? Well, notice it has a discontinuity at 1, right? We have this vertical asymptote at 1, so it's discontinuous at 1 because of that vertical asymptote. So the answer is no. Okay, what about this one? Now you need to zoom in a bit to see this. Is this continuous? Determine whether the function is continuous on the interval -6 to 6. Right, so if we go all the way -6 to 6, is this continuous everywhere? No, there's a bad spot at -4, right? Function's not defined at -4, so it can't be continuous there. So it's not continuous on that interval from -6 to 6. Okay, as long as there's even one point in that open interval -6 to 6 where it's discontinuous, then the function is not continuous on that interval. Okay, what about here? Is this function continuous on the open interval -5 to 5? Well, again, notice we have a bad point at x equals 1. So it is continuous really everywhere except at x equals 1. But that's a bad spot, so it's not continuous on the whole interval -5 to 5. So the answer would be no. Okay, now one last problem. Determine the value of the constant k for which the function f of x is continuous at -3. So we have this function here. It's a piecewise defined function. It's defined to be this when x is not -3. Notice when x is -3, this doesn't make sense here. And when x is -3, we're going to define it to be k. But the question is, what should we make k be in order to make this function be continuous? So let's remind ourselves here of the definition of continuity. Here's a formula for our function. Recall f is continuous at a number, so x is continuous at -3 if f of -3 is defined. And notice it is defined. F of -3 is going to be k. Now we have to figure out what k is going to be, but it's going to be defined. Does the limit as x approaches negative 3 of f of x exist? Well, yeah, we can find that out. And then not only that, not only does this limit have to exist and this function value have to be defined, these two things have to equal each other. That's part 3. In fact, part 3 kind of encapsulates parts 1 and 2. In other words, if f of negative 3 has to be defined in order to be able to say this, and this limit has to exist in order to be able to say this. So it really all comes down to this right here. So how can we check this? So the question is really, what's the limit as x approaches negative 3 of f of x? Well, notice as x approaches negative 3, remember the limit has nothing to do with how the function is defined at negative 3, only how it's defined near negative 3. And when we pick values of x that are different from negative 3, the formula is just going to be this. When x is negative 3, it's this. But when it's different from negative 3, it's this. So my point is when we say what's the limit as x approaches negative 3 of f of x, we can just say that's the same thing as the limit as x approaches negative 3 of this. Okay, this would be the same thing as the limit as x approaches negative 3 of x squared plus 8x plus 15 over x plus 3. Now, how do we compute this limit? Well, this is what we talked about in the last module. The way that we compute this limit is we're going to factor, right? And I think we'll have a x plus 3 factor in both the numerator and the denominator. In fact, the numerator factors to be x plus 3 times x plus 5. And so notice these cancel and we just get the limit. Scoot down so you can see it here. The limit as x approaches negative 3 of x plus 5. And now we can just plug in the negative 3, and we plug in negative 3, we get negative 3 plus 5, which is 2. So notice this limit is 2. Okay, so this limit right here is 2. So we want f of negative 3 to be 2. Well, what is f of negative 3? F of negative 3 is k. So the point is we want k to be 2, right? We want k to be 2. If k is 2, this function is going to be continuous. In fact, let's look at this function in Desmos. We have this function f of x equals this. Now, remember when this simplified, it simplified to just be x plus 5. And notice this is really the graph of x plus 5. Now, one thing that's a little annoying about MyMathLab is it doesn't show the hole here. There's actually a hole at negative 3. It shows it if you drag on it and you get to negative 3. So f of negative 3 is undefined for this function. But notice how high is that hole, right? Notice it's at a height of 2. In fact, if we were to plot the point negative 3 comma k, let me plot this here. And I'm going to take different values of k. I'm going to use a slider for k. By the way, let me put in the hole right there. So the way I put in the hole is I just defined a point and I use this right here. I was actually able to kind of force it to put the hole in there. But notice what value of k do we need to have in order for this hole to be filled in? In other words, for us to have a continuous function, right? Like if k is 4, well, notice this is not a continuous function. This would be the graph of our function f if k were 4. And notice, is that continuous? No. In fact, let's go back to our function here. If I let k be 4, what does the graph of this function look like if k were 4? Well, the graph would look like this, right? What if I let k be 5? Well, then the graph would look like this, or k be 0. Notice, this is not a continuous function. I need k to be 2. I need k. In order to be continuous, this has to fill in that hole. So in other words, the limit as we approach negative 3 was 2. So we want f of negative 3 to also be 2. Okay, so for this problem, essentially what you need to do is just take the limit as x approaches negative 3 of this, and then that's what your k is going to be. So our k is 2 here. So that's a little bit of a tricky problem. But that's making sure you understand the definition of continuity.